So welcome everyone. This is our 14th live stream geometry session. So here we have Ram and Anmol with us for now, and more will probably join later. And this time I took two of them from the Benelux Math Contest. So that's for Belgium, the Netherlands, and Luxembourg. So they're kind of like a partnership of 3 countries. It's kind of very similar to the Baltic Way. So that one was Estonia, Latvia, and Lithuania. This one's Belgium, the Netherlands, and Luxembourg. So those are my first 2 problems. And then the next 4 problems I chose from the China Southeast Math Olympiad. So I'm gonna share my screen. Just 1 second. All right. Can you guys see the first question? So this is a 2 circles question. All right. So yeah, I didn't do a lot of 2 circles questions in the beginning of my channel, but I've done some more over time. So we have 2 circles, gamma 1 and gamma 2, and they intersect at A and Z. And they have centers B and C. So I'm just trying to think how I want to draw this. I will do it like this. Something like that. I don't want them to be the same size necessarily. Z is the other intersection point. All right. Then we take the exterior angle bisector of BAC. So I'm just thinking how I want to draw that. I could do it like this, I guess. So obviously the exterior angle bisector is perpendicular to the interior angle bisector. And then, so it intersects the circles at X and Y. So that's X, this is Y. And we want to show the angle bisector of BZC passes through the circumcenter of XYZ. Okay, so I'm going to draw the circumcircle of XYZ. Hold on just a sec. Let me decide what I want to hide and what I want to keep. Yeah, how do I note that this is like, yeah, let me do it like this. So I'll draw this point and this point, just so that you know it's like the exterior bisector. Okay. And then I want to draw the circumcircle of XYZ. Here's my circle. And there's the circumcenter. Basically, we want to show the angle bisector of BZC passes through G. All right, let me try to make the diagram a little nicer. So ABZC is a kite, obviously. Yeah, let me shrink some stuff just so it looks a little better and doesn't overlap the question. All right. So how do we show the angle bisector of BZC passes through G?
Seems like X, F, G are collinear.
X, F, and G are collinear. Yeah, it does look like it. Hey, Hakan, thanks for joining. So Hakan's from Turkey, and he just recently asked to join the session, so welcome. So yeah, you can either just type in the chat or you can speak on audio, either way. So yeah, currently you're on mute, but whatever you would like is fine. All right, so that is interesting. It looks like X, F, and G are collinear. Thank you. Thanks for joining. So it looks like X, F, and G are collinear, and G, E, and Y are collinear. Is that? Let's see why that's true. So if that were true, then would that solve the problem? So, oh, that's interesting. B, Z, C. Yeah, so if we knew that, could we use that to solve the problem? Not sure. But yeah, first let's see, yeah, how could we show X, F, and G are collinear? So yeah, we have to use the fact that this is the external bisector. So yeah, I think it's worth extending EB and FC to meet the circles. So, whoops. So I'm going to draw this point and this point. Okay. And basically, so since this is an angle bisector, arc XF is equal to arc XH, and EY is equal to YI. So yeah, X is the midpoint of this arc, and Y is the midpoint of this arc. And AH is a diameter, and AI is a diameter. So yeah, HI is parallel to BC. And I think HFEI might be cyclic. Let me check. Yeah, and I think this is also cyclic. Ooh, and it passes through Z too, it looks like. And we could probably prove that using power of a point, I'm guessing. Yeah, so let's see. I'll hide D for now. Whoops, let me unhide that. So yeah, we have a couple cyclic quadrilaterals. So it's interesting. BF, Z, C, and E look like they're cyclic. Is that tangent to the other circlet Z? I think it might be. Oh no, it's not tangent. It kind of looks like it, but yeah, you can see it's not tangent there. So what? So let's think about that. So why would that be cyclic? Well, I think, yeah, we can use an angle chase, I think, to show FHIE is cyclic, because this angle, AZ is the bisector of GZF. HFA and HEA are both 90. Yeah, so that solves it. So yeah, so like Akan said, HFEI is cyclic, but so by power of a point, HA times EA is IA times FA, but then BA is half of HA and CA is half of IA. So we also know FBCE is cyclic. And then, yeah, by an angle chase, we can also show that Z lies on that circle. So FBZCE is cyclic. So yeah, thanks for that idea, Hakan. I think Ram is maybe saying GZ. Let me check. So if I use the angle bisector, I take the angle, oh no, G is the circumcenter of XYZ. So it's the center of that circle. Oh, G is right here, sorry. Yes. All right, so if BZ, let's see. I'm going to draw that circle just to help us. We want to show G lies on that circle also, and we also want to show that G is the midpoint of this arc. Is it obvious that G lies on the circle? I guess it's probably just an angle chase, right? So we can use an angle chase to show Z is on that circle. And then for G, how do we know G lies on that circle? G looks like O to me. Oh, there actually is no O, but I think, yeah, if your computer is a little blurry, the O is probably the G. They're probably the same point. Yeah, I'm just trying to think how we show that lies on the circle. Yeah, if we could show XFE and GEY are collinear, maybe that would help us do it using an angle chase. Let's see. So maybe we can use an angle chase to show XF and G are collinear. So if we can show angle AXF equals angle AXG, that would do it. And AXF is the same as AZF. And AXG is YXG So yeah, so I'm thinking about how to show XF and G are collinear. So angle AXF is AHF, maybe that would help, which is 90 minus FAH. Oh, I think I might have it. Is angle XZY equal to angle BZC? I think so. Let me check. So angle XZY, 129, or is that what, did it say 129? Whoops, 109, and angle BZC is also 109. Yeah, so yeah, I feel like there's probably a simple way to see that. So XZY is XZA plus YZA, which is XHA plus YIA. Yeah, so we can use an angle chase to show that. I think there's just a lot of angle chasing here, but I think eventually, I think we can use that to show X, F, and G are collinear. So I'm gonna type this out later, but yeah, we can show X, F, and G and Y, E, G are collinear with an angle chase. And then we want to show G is the midpoint of arc BGC, and I think that's also just an angle chase because we just need to show angle GEB is equal to angle GFC. All right, so a lot of angle chasing here, but I think I see the solution. So I'm going to delete some of the stuff I added. All right, just going to minimize this for now. Hold on just a sec. So yeah, there's a lot of angle chasing here, but it eventually solves it. All right, so what should I do? I will delete this circle. Let's see. Yeah, I'll just leave everything like that for now. All right, so let G be the circumcenter of triangle XYZ. All right, and then first we want to show FBZCEE is cyclic, so I'm going to use Hakan's idea. So, I'm going to say extend AB. Now I'll just say define H and I as it looks in the diagram. So basically, we have angle HFI is equal to angle HFA is equal to 90, which is equal to angle AEI, which is equal to angle HEI. So that was Hakan's idea. Let me change this to an I. And so that means HFEI is cyclic. All right, so by power of a point, HA times AE is equal to IA times AF. But HA is 2AB. IA is 2AC. So that means that, I'll write it like this. HA is 2BA, IA is 2CA. And so that means that BA times AE is equal to CA times AF. And so BFEC is cyclic. And then we want to show that passes through G. Actually, first I'm going to show it passes through Z. So that should just be an angle chase. I'm trying to remember how I did that. So yeah, so we have angle BZC is equal to angle BAC, which is 180 minus angle BAF, which is 180 minus angle BFA. And so basically that means BZCF is also cyclic. So that means that BZCEF is cyclic. That's because BZC plus BFC is 180. And then I'm going to show that G lies on that circle. But to do that, first I'm going to show that G, F, and X are collinear. So, angle, yeah, let me write it like this. So we have angle GXA is half of 180 minus angle XGY, because XGY is isosceles. And an angle XGY is, so I'll write it like this. So that's 90 minus half of angle XGY. And half of angle XGY is like if you have a point on this arc, it would be that angle, which is 180 minus angle XZY. So that's 90 minus half of 180 minus angle XZY. And that simplifies to just half of angle XZY. And XZY is XZ. Wait, I think I messed up somewhere. So wait. So GXA, that's half of 180 minus XGY, which is 90 minus half of XGY, which is, oh, this is just 90 minus 180 minus XCY. So this is XCY minus 90. And XCY is XZA plus YZA, which is XHA plus YIA. I thought I had this for a second. So we want to show XZY minus 90 is both GXY and GYX. No, I'm sorry, that's FXA. We want to show that. FXA. So yeah, I think I just have to continue this angle chase. That is angle XZA plus angle YZA minus 90, which is angle XHA plus, yeah, this, so let's see where this goes. Yeah, okay, so, but XHA is equal to, I think XHA is equal to YIA because XHA is 90 minus XAH and YIA is 90 minus YAI, but these two angles are equal since this is a bisector. So yeah, this is a kind of long angle chase, but maybe there's a way to simplify it. And so YAI is equal to FAX. All right, so I'm gonna write this out first, but yeah, I'm gonna want to break it up into a couple lines. See if it works. Let's see how this comes out. All right, let me break this up. All right, let's see. So XAH plus FAX. Yeah, what am I doing here? So this would be 90 minus angle FAH. Yeah, okay. So this is kind of complicated, but it gets the job done. So that's equal to 90 minus angle FAH, which is equal to angle FHA, which is equal to angle FXA. So this is a long way to show, but if angle GXA is angle FXA, then G, F, and X are collinear. So G, F, and X are collinear. And then similarly, G, E, and Y are collinear. So I'm positive there's probably a way to simplify this, but this is how I'll do it for now. Let's see. And so then we want to show, then we can show G lies on that circle, the BFEC, because, how did I show that? Angle FGE is 180 minus FB or FZE. Yeah, I had an idea for how to do that. Let's see. I mean, I think it's just an angle chase to show that G lies on this circle, BZ, CEF. I'm just thinking the fastest way to write it out. Okay, so I think I have an idea. So we have angle FGE is equal to angle XGY, which is 180 minus 2 angle FXA, which is 180 minus 2 angle, so FX, this should be FXA. That's 180 minus 2 angle FHA. And then it's easy to show that that's angle FBA. Or 180 minus angle FBA. And so that means that FGEB is cyclic. And then also the C and Z also lie in that circle. So I'll just put them all at once. So BZCEGF is cyclic. BZCGEF is cyclic. So yeah, I'm running out of room here, but I think I will be good eventually. So we have this where's my circle tool? All right, so all those points lie in a circle, and it's not hard to show G is the midpoint of arc BGC, because angle GEB is equal to angle GFC by an angle chase. So I'm running out of room, but I will maybe write it up here. So we have angle GEB is equal to angle YIA, which and then YIA is 90 minus YAI. Yeah, I see how to do it. I'm just making it maybe more complicated than it has to be, but let's see if there's a better way to say it. Yeah, I'll just write it like this. So YIA is 90 minus YAI, which is 90 minus angle EAY, which is 90 minus angle XAH, which is angle XHA, which is angle GFA. And so that means Yeah, there we go. So all the way up here, I have that calculation. So if angle GEB is equal to angle GF, I'll just call it GFC instead of GFA, then that means that arc GB is equal to arc GC. So basically that means G is the midpoint of arc BGC. And that means that since this is cyclic, the bisector BZC passes through G, which solves the problem. That was a little trickier than I thought. There was just a lot of calculation, and I'm sure there's like a way to simplify all that calculation. But yeah, does that make sense to everyone? All right. I'm going to move on to the next problem. That was a cool one. Let's see. All right, so here's another problem from Benelux in 2016. So Belgium, Netherlands, Luxembourg. So we have a triangle ABC and we have a circle that passes through two of the vertices. And it intersects AC. Okay, so I'm just gonna do it like this. Let's see. There we go. That looks a little better. All right, so it intersects AC at B and AB at E. On the ray from B through D, so let me draw that ray. Where's my ray? Here we go. Lies at point K such that BK is equal to AC. So we want BK equal to AC, and we want CL equal to AB. That's kind of, so there's this compass and straight edge tool, which is pretty convenient. So AC is the length I want. So this is BK, this should be point K. All right, so I'm gonna hide the circle. And then I will use the compass tool to get point L. So CL is equal to AB. All right. So isn't that cool? You got a little compass compass tool. So CL. All right. And let me hide some stuff. I want to hide all of it. All right, we want to show the circumcenter of AKL lies on omega. That's an interesting fact. Let me draw that circumcenter. This looks isosceles, AKL. So I think we'll have to prove AKL is isosceles. So lucky for me, GeoGebra makes things easier. But that doesn't look true. Maybe I'm missing something, but maybe it is. Yeah, maybe the circumcenter is just low on the triangle. So if I draw that circle, see, yeah, okay, so it does lie on it. But yeah, first let's see, because this definitely looks isosceles, right? Yeah, so maybe there's some congruent triangles here. So BK is equal to AC. So maybe BKA is congruent to ACL. Is that true? I'm not sure if that's true. Is BKA congruent to ACL. Only if, I don't think so actually. Oh, it is true. BKA is congruent to ACL. Oh, but is it side angle side? Let's see. So let's see. BK is equal to AC. And CL is equal to AB. So side angle side. Yeah. Okay. So that's why AKL is isosceles, because BKA is congruent to ACL. Let's see. F looks like the midpoint of arc BC. Yeah, so basically we want to show the midpoint of arc BC is the circumcenter. Again, GeoGebra is helping me a lot here, right? Because it would be harder to notice those things without GeoGebra. So if I let F be the midpoint of arc BEC, how do I show it's equidistant, or how do I show it's a circumcenter? It's interesting. I'll be right back, guys. Just a second. All right, thanks for waiting. So let's see, let's check it out. I wonder if so ALK is isosceles, FBC is also isosceles. Let's see. Yeah, I wonder if there's a way to like label the equal segments. Maybe we'll just have to keep it in our mind. So BAK and ACL are congruent. We'll just have to memorize that. So if they're congruent, then that means if you draw the angle bisector of LAK, yeah, so I'm going to draw the angle bisector of LAK. Let's see. So BE is equal to CF. BD or BK is equal to AC. So I think BFD might be congruent to CAK. Is that true? No. No, that's not true. But if we flip triangle, wait a sec. BAK CAL. Something's weird here. So angle LAD is equal to LKB. I feel like I'm close, but yeah. Let's see. So yeah, we've shown this as isosceles. If we can show angle LFK is twice angle LAK, yeah, I think that might do it, right? So is FLC congruent? No, I was going to say FLC is congruent to FBK, but that's clearly not true. Is FLC congruent to FAB? That looks plausible. So yeah, we want to show FLC is congruent to FAB. And that might just be like side angle side or something. Yeah, FLC I think is congruent to FAB. I think that solves it. Let me start typing it up. Okay, so yeah, I don't even think we need AL is equal to AK. Just as long as you know FLC is congruent to FAB. Is that true? I think it's true. Yeah. But hold on a sec. So I said FLC is congruent to FAB. That's 22 degrees. That's 22. Yeah. That should be an angle chase. Okay. So I'm going to delete that. Actually, I'm going to draw it. So yeah, we just don't know it's isosceles, but so I'll just say let F. Actually, no, I will delete the circle. I just want, or I'll hide the circle. I just want F to be the midpoint of arc BEDC. Okay. Maybe I'll just move the diagram over a tiny bit more so you can see it as I type. So let F be the midpoint of arc BEDC. And then I said, I'm trying to show ABF is congruent to CFL. So since F is the midpoint, we have BF is equal to CF. I could draw those in, I guess. And we also have AB is equal to CL from the problem statement. And then we want to show the angle between them is equal. So angle ABF is equal to angle EBF, which is equal to angle ECF. Is it that simple? I think it is, yeah. So, oh no, we want to show angle ABL. What am I showing? BF. ABF, I want to show that's FCL. Yeah, so angle ABF is equal to angle EBF is equal to angle ECF is equal to angle LCF. And so ABF is congruent to FCL. And so that means that FA is equal to FL. And then by the same argument, FA is equal to FK. And so F is the circumcenter of triangle AKL. And so the circumcenter, oh, I called it F. I could just say F equals O. Tell you what, I'll say F equals O is the circumcenter of triangle AKL. So therefore, O lies on omega. All right. That was a fun one. So let's hop to the next problem. All right. So here's a cyclic quadrilateral problem. So ABCD is a cyclic quadrilateral with perpendicular diagonals. So I'll do it like this. We want AC is perpendicular to BB. Okay, so let me move this around. So AC is perpendicular to BB. M is the midpoint of arc ABC. Let me hide this. So I will do that by using the perpendicular bisector tool. So this is M. O is the center of the circle. So hold on just a sec. So O is equal to the center of C. All right. So OM is perpendicular to AC. So maybe I'll just leave OM there and hide the rest. The circumcircle of DOM, let's draw that. It intersects DA and DC at E and F. Okay, it's hard to see both intersections. Let's see. That looks a little better. So DA at E, DC at F. We want to show BE is equal to BF. That's kind of interesting. I'll bet you it's like congruent triangles again somehow. Is AE equal to FC? Let me check that. Where's my measure? 2.6. Yes. Oh man, I'm getting good at this. So I wonder if, yeah, but AEB doesn't look congruent to BFC. At least I don't think so. But if AE is equal to FC, I wonder if A angle, no, I don't think that's true. I was going to say maybe angle AEB is equal to angle BFC, or 180 minus that, but I don't think that's true. Let's just draw those for fun. But yeah, that's interesting that AE is equal to FC. I feel like there has to be a, I don't think it's a coincidence that those were equal. It's only one decimal place, but yeah, no, that has to be true. Okay. So why does AE equal FC, and why does that mean BE equals BF? Yeah, so that would mean that if I extend, if I extend BE and BF to meet the circle, is ME equal to MF? Let's see. Yes, it sure looks like it. Yes. So that would mean MEBF we want to show as a kite. So let's see. So is MEA congruent to MFC? I think that's probably what we have to show is true. Yeah. So if we can show AE equals CF, then I think we can show triangle MEA is congruent to MFC. Okay. Oh yeah, I kind of erased segment BD, but let's see. So yeah, can we show MEA is congruent to MFC? So maybe we could use angle side angle. Yeah. Well, so okay, I think. I think using angle side angle, we can show those are congruent. Because yeah, MA is equal to MC. So yeah. So I think angle side angle shows MEA and MFC are congruent. And so ME is equal to MF. And then if we know that, is it clear that MEBF is a kite? So we want to show MB bisects angle EMF. I think that's probably true just by an angle chase. Because we want to show, because MAC is isosceles and MG is perpendicular to AC, and then MEF is isosceles, and we want to show MB is perpendicular to EF. So that looks, I think that should be an angle chase. Okay. Yes. So I think we've solved it. So we're going fast today. All right, so I'm going to write it out. Yeah, if we get through all 6 before 3 hours, I might look up a couple harder problems. Okay, so basically we have MA is equal to MC. And then we have angle MAE is, so I want to show MEA is congruent to MFC. So what was I thinking here? I forgot. Yeah, so MAE is equal to angle MAD, which is equal to angle MCD, which is equal to angle MCF. And then we also have angle MEA is 180 minus angle MED, which is 180 minus angle MFD, which is equal to angle MFC. Okay. And so from there, we can, from there, angle, since two of the three angles in those triangles are equal, the third also has to be equal. So we have angle AME is equal to angle FMC. And so those triangles are congruent by angle side angle. So by angle side angle congruence, triangle AME is congruent to triangle CMF. So ME is equal to MF. All right. Whoops. And then I'm going to show that MB is perpendicular to EF. And that really should just be an angle chase because I'm just trying to think about the best way to write it. I thought it was an angle chase for a second. Can we show angle MFE plus angle FMB is 90? How did I think to do this? Thought I had an idea. So MBF is equal to MCF. Yeah, is equal to M. Oh no, MBF isn't necessarily MCF. Okay, so, but even still, I think there's like, yeah, it should be an angle chase. I'm just, yeah, what's the best way to write it out? So we know MG is perpendicular to AC. And so if we can show the angle that MB makes with MG is the same as the angle EF makes with AC, that would be done. Have we used the, yeah, this is where I'm trying to use that fact in this angle chase right here. So yeah, you're right. We do have to use that, and this is the part where I'm going to use it right here. Just thinking of the best way to do this. So MFE. So EMF is the same as AMC. Let's see. Is BEDF cyclic? No. Let's see. But yeah, I think so. I'll just write out the idea I had. There might be a simpler way than this, but this is kind of the idea I had. So I'm going to let EF meet AC at a point H. There we go. So basically, I'm claiming if we can show angle FHC is equal to angle BMO, then that should solve the problem. And BMO is the same as MBD. So all right, so this is a little complicated, but yeah, we'll just have to remember that H is that point out here. So so we have angle FHC is equal to angle FCA minus angle BFE, which is hey Enrique, thanks for joining. So yeah, we are on our third problem here. So yeah, we've gone kind of fast today, but well, it's actually a little over an hour, so I guess that's not super fast. But yeah, good to see you. So angle FCA minus angle DFE, and that's angle DCA minus angle DFE. So, and then we have angle OMB is equal to angle MBD, which is equal to angle MCD. So an MCD, let's think about this. So basically we want to show this as angle MCD, which is true. So DFE, I just did a quick angle chase in my head buffer. Can we show that this is MCD? So DCA minus DFE. So that's DFE is DFM plus MFE. Let's see. Yeah, I think I'm kind of going in circles here, but I have an idea. We want to show that this is MCB. Can we show angle DFE is equal to angle MCA? I think that's what we need. Let me check that. DFE is 66.5, MCA. Oh no, that's not true. What was I thinking? or is DFE DCA? No. Now I'm just confused. FHC is, let's see, FHC is DFE, yes, it should be. So it should be DFE minus FCA, you're right. DFE, thanks for pointing that out. And DFE, that's DFE minus DCA. Okay. And we want to show that that's DCM. So is DFE minus DCA equal to DCM? So let me think what that would mean. So yeah, DCM is DCA minus MCA. I'm just going to write some of this out. So we have angle BMO is equal to angle MGD. So that's where we use the fact that they're perpendicular. Or I'm sorry, MBD. And that's equal to angle MCD. And that's equal to angle DCA minus angle MCA. So we want to show those two are equal. Yeah, can we show that this is equal to this? So that's the same as saying twice angle DCA is DFE plus MCA. So that means DCA is the average of MCA and DFE. Interesting. So DFE is 180 minus DME, and DME is equal to CMA. So I think we're very close here. So I'm gonna and DME is equal to CMA from the congruence that we said earlier. So that should be 180 minus angle CMA minus angle DCA. And CMA is CDA, right? Yeah. So we want to show these are equal. So CMA is the same as FDE. I think did I just go in a circle? Something's weird here. Let's see, FHC, it's DFE minus FCA. That sounds good, which is DFE minus BCA. And then DFE is 180 minus DME. Okay. And DME is equal to CMA. That looks right. And CMA is equal to CDA. So this is, now I'm really confused. I thought I had it, but I was wrong. Let's see. Okay, I think I might have a better way to do this. So angle BMF, it's 180 minus angle BCF, which is 180 minus BCD. Yeah, okay. I have a better way than doing this. All this. Let me delete this. So this should be a better way to do it. We have angle BMF. Oh wait. Never mind. Let me add that back. Yeah, let me try something different here. So angle BMF is equal to angle BMD minus angle BMF, which is equal to let's see, that's angle BAD minus angle DEF, which is equal to angle BAB minus angle HEA. Which is equal to Yeah, I feel like I'm kind of going in circles, but there has to be a way to angle chase this to finish it. I'm like sure of it. So let's see. Does CMA equal EMF? Let's see. Yes. So this. Oh, DME is not equal to CMA. Yeah, this isn't true right here. That's where I got confused. So let's see. We want to show that this is equal to this. So 180 minus DME minus MCA. So yeah, so this is equal to 180 minus angle DMF plus angle FME minus angle VCA. And then FME is equal to CMA. So let's see. CD MCD is yeah, we want to show these are equal. So twice angle DCA is arc DA. So we have CMA. Yeah, this is trickier than I thought. Let's see. But yeah, we're really close here. Wait, maybe is MFHB cyclic? Oops. No, but MFHC is cyclic. But I think, yeah, what if I draw in this segment? Then yeah, I like the strategy. It just got complicated. MBD. Maybe saying MBD is equal to MAD would be easier. Not sure. MCD. We can get FHC is equal to BM. Okay, so FHC is equal to CMF. Okay, so if we know MHCF is cyclic, that would basically solve it. And we kind of do know it's cyclic because we can show angle MFE is equal to angle MCA. So then you're saying that would mean FHC is equal to CMF. CMF is equal to MAD because they're congruent. MAD is equal to MBD. Yeah, okay, so that does it. Let me see if there's a better way. So is HADM cyclic? That kind of looks more like a parallel. No, because AD and M lie on a circle, but H doesn't lie on that circle, so that couldn't be cyclic. But Hakan has a solution. CMF equals MAD. Wait, you're saying CMF? But yeah, does ME equal? Whoa, we missed that. Wait, because that would like, ME is equal to EA. So we really missed something important previously about this. Interesting. All right. Because yeah, that's so weird. AE is equal to ME. I did not realize that. Hmm. Okay, let's see.
Look at triangle MAE and MDC, or maybe MCF.
MAE and MCF.
And don't they seem congruent?
So since AME is congruent to CMF, angle MAE is MCF. Yeah, MAE is equal to MCF, but is MCF equal to AEM?
How can MAE be equal to MCF? We are DFC collinear. Yeah, DFC collinear. Yeah, makes sense.
Yeah, DF and C are collinear. But basically it turns out that EA is equal to EM. And FM is equal to FC, which I didn't realize earlier. But that seems pretty important, and I don't know why that's the case. Interesting. So yeah, we want to show BM is perpendicular to EF, which is the same as saying BMF plus MFE is 90. Have we used the fact that this circle passes through O? I don't think we have. Well, so MFE is MOE. Yeah, I think we haven't, maybe we haven't used that this circle passes through O. So OM is equal to OD. And so that means angle, so that means we have two equal arcs, right? So angle DFO is equal to angle MEO. All right, let's see. So Hakan had that proof if we know that ME is equal to EA. Basically, we're saying that BE is the angle bisector of ABM, right? Oh, wait, not necessarily. Wait, I'm not sure. I'm actually not sure if AM is equal to ME. Maybe it just looked like it. It sure looks like it, though. Let's see. I would be pretty surprised if that wasn't true and just looked true. So, but if AM is equal to ME, oh, but that doesn't necessarily mean BE is the angle bisector of AME. Okay. So yeah, what would that mean That would mean that angle MED is twice angle. Oh, and that is true. Yeah, because angle MED is equal to angle MOD, which is half of angle MAD. So AME is isosceles. So we do have a proof. I wonder if we can simplify that proof. Yeah, so I have a proof that ME is equal to EA. So if ME equals EA and MF is equal to FC, then AE is equal to FC, and if AE is equal to FC, can we use that to show BE is equal to BF?
Law of sines or something?
Possibly. Because sine, yeah. Maybe Pascal's theorem or something? No, I don't want to use Pascal's here. Yeah, maybe I should just go ahead with what Hakan said. I'm just going to type out what Hakan said. So hold on a sec. Let me erase some of this. Whoops, not all of that. Okay, so basically we have angle MED is equal to angle MOD, which is equal to twice angle MAD. So that implies that ME is equal to AE. And then similarly, MF is equal to FC. I'll write it like that. MF is equal to CF. Okay, and so so we know MFCH is cyclic because just trying to think the best way to write it, but basically angle MFH is equal to angle MFE, which I mean, so MFE is similar to MCA, or I could write it like that, like this. So that's okay. Let me split this into two lines. It's probably not going to fit on one line. Okay, like that. Maybe it would fit on one line. Let me check. Ah, that fits on one line. Okay. So MFHC is cyclic. So we can draw that in. And then now I'm going to write what Khan said. So we have, oops, angle FHC is equal to angle CMF. Is equal to angle MCF, which is equal to oh, I could try that. Try using line break the next time. He says FHC is equal to CMF is equal to MAD. Why is CMF equal to MAD? I'm trying to understand that. I think it's because CMF is equal to MCF is equal to angle MCD is equal to angle MAD. Equal to angle MBD is equal to angle BMO. I think this does it. So basically, if angle FHC is equal to angle BMO, then BM has to be perpendicular to FH. So I'll type out a little mini proof of it, but yeah, how do I? I'm just thinking how to express that. But basically I'm thinking OM is perpendicular to AC. So that would imply BM is perpendicular to EF, since the angles between them are the same. Well, let me see if there's like a way to express that better. So So FHC yeah, do you guys kind of see what I'm saying? So FHC, that's the angle between EF and AC, and BMO is the angle between BM and MO. So if the angles between them are the same, then if one of them is perpendicular, the other also has to be perpendicular. That's kind of my thought process here. How do you write that out though? I'm not sure. So but there has to be a way to write that out in terms of what if I draw in this? So FHC is equal to BMO. Yeah, what if I think I need this point right here. So
then MIGH is cyclic.
Yeah, okay. So and that would solve it. Yeah, so Yeah, let me write it out like that. So I don't even know if you need cyclic. I think you could do an angle chase, like you could say angle HJC is 90 minus FHC, and HJC is MJI, which is, yeah, so yeah, basically, yeah, so I'll write it out like this. So angle MJI plus angle JMI is equal to angle FJG plus angle JFG, which is equal to 90. So that means that MI is perpendicular to JI. So BM is perpendicular to EF. And so that means that BE is equal to BF, since ME is equal to MF. All right, I think that is probably good for now. I'm sure there's like easier ways to express certain parts of this proof, but that does the job for now. All right, let me just add in this. So one more step. So JMI plus MJI is that's angle BMO per just because I'm OCD. All right, so I'm going to move on to the next one then. Thanks everyone for the help on that. So this is our fourth.
Hey Michael.
Hey,
so
Sai.
could you turn back the question? Yes. So could you turn back the question? I actually came to here quite late. So just if you could give me a small little explanation.
Yeah. So do you want me to start from the beginning?
Yeah, if it takes a lot of time, then we may move to the next question. I'll watch the recording.
But yeah, so I'll just go over it really quickly. So ABCD is like a cyclic quadrilateral where the diagonals are perpendicular, and O is the center, and then M is the midpoint.
Yeah, I got the question.
Oh, you got the question. Okay.
Yeah.
So yeah, first we showed that triangle AME is congruent to triangle AFC, or I'm sorry, AME is congruent to CMF. So that was step one. Then step two is showing that AE is equal to ME and MF is equal to MC. And we did that using an angle chase here. And then I added in this point H. I don't even know if I really needed this point H, but then I just did an angle chase that eventually solved it. So there was a lot of angle chasing here. I'm not going to go through all of it, but yeah, you can see it on YouTube.
Yeah, sure.
All right, sounds good. Or yeah, you can email me or look at it on Discord if you want.